extremely uniformly spread in the early universe. And so it has to gather up by the gravitational forces from the dark matter particles into this cosmic web. And so during that time, they're slowly drifting, collapsing into clouds. First it was uniform, then it aggregates into clouds, and those clouds are drifted into the gravitational potential wells of this framework of matter that's kind of invisible, but is there gravitationally. And that just takes a long time to happen before you can get the first generation of stars. And it's only those really rare fluctuations that have, instead of having just the average, they're way out in the tails of the distribution curve. They begin to form the first stars and galaxies. And so in that simulation, those little peaks appeared first. So during the dark ages, the matter is cooling and expanding and being able to collapse a little. The universe is expanding, and it's the gravitational fight against the expansion and the thermal history that's going on, but it cools fairly quickly. It can form into clouds, and those clouds then can pull into the gravitational potential of what is going to be a galaxy, a dark matter halo. And then when enough clouds fall in there, you can get enough to shock and have collapse and have first generation of stars happening. So you have the hope of looking in that region because most of the clouds are made out of hydrogen, and eventually the single atoms of hydrogen combine to make H2, and there's a 21 centimeter wavelength line from that in the rest frame. So you can actually try and look for that. If you can find a radio quiet location on the Earth, you can look for that radiation from the early universe and try and map how that behaves over time. And because the universe is expanding, you can separate out the times by just what the wavelength has been shifted to. So even though it's the dark ages, it's dark invisible light at the time. It's not dark in radio and other things. There's the radiation from the beginning of the universe, and there's the radiation from the hydrogen lines, and there's a little bit of helium and so forth. So during those dark ages, it's kind of like the history we call the Dark Ages, during the collapse of civilization in Europe was the Dark Ages for science, and that's when the Muslim cultures were carrying bringing astronomy back up and building algebra and carrying that kind of stuff. But it was called the Dark Ages in Europe because a lot of knowledge was lost, and it was only by getting to the Muslim and Arabic and Egyptian libraries that a lot of knowledge was recovered. The dark ages in the universe, it's just dark, right? I mean, it's a little misnomer, but for a while people were sort of desolate that there might not be easy ways. But now we have come up with schemes where we're going to try and do observations of that region. But what's happening is you just need the opportunity for something that's as uniform as a glass of water to begin to coalesce so you can finally find galaxies. And that process is interesting. And we do now know that large hydrogen clouds form, and they don't stay uniform, right, and just coalesce in. They actually collapse into clouds. They separate into sort of more vacuum, fairly high vacuum, and then fairly more dense clouds. And we can see that because when the very first galaxies start up, the center of the galaxies is very bright. We call them quasars. And you can see the light from the quasars, and you can see the light absorbed by the hydrogen coming in between. There's the first line in hydrogen is called the Lyman alpha line, or one of the first lines. And you can see what's called the Lyman alpha forest. You can see this whole host of clouds that haven't yet clumped into galaxies that are between us and the very first galaxies that are turning on. And you can see later on they go away and they're just galaxies. So we're actually beginning to have some hint about what's going on during the dark ages. Right now, it's not the deep dark ages, it's just towards the end of the dark ages. And eventually the universe goes to where between us and the galaxies, the space is pretty much got a vacuum in it, and there's the little bit of matter in it that's completely ionized. That is, the electrons are stripped back off again, whereas earlier they were neutral atoms, right, in order to collapse and form stars. So we know something about what's going on in the dark ages. It's a less interesting time if you're an astronomer because it's harder to see, and I'm focusing primarily on the early universe, but I am doing some other research, which is I have a couple of postdocs and a couple of students who I've hired to try and look at light from these very early stars and very early galaxies. And that light travels, and as it travels, it tries to go in a straight line, but space-time is slightly curved by the intervening matter and energy, which is mostly dark matter. And so you can try and map the location of the dark matter by looking for the fact that the light is slightly deviated, and that creates this change in the shape, the brightness and the shape, and you can hope to map the intervening material in a really straightforward way. So we can learn about the dark matter even more than what we know now and from the simulations.
Okay. So the dark matter that you're talking about is basically the black holes, the very dense material, or is it something else that doesn't emit anything else?
There was hope among astronomers that it was just gas and stars yet to be born. And then when that got to be shown not to be the case, by careful observation, one of the things you can do is look at the nearest small galaxy to us, the Large Magellanic Cloud, where you can monitor with one telescope 1 million stars night after night, and you can see if the material passes in front of them, and you can then you can limit how many objects could be going between us and them, and therefore how many objects there are in our own galaxy to explain, you know, the orbital properties of the stars around the galaxies and so forth, to explain where this dark matter might be. And you can show that it isn't ordinary objects that are compact, stars that didn't quite turn on, right? They're like Jupiters, or black holes, or other things. The black holes bend the light, and you would see the effect from that. So you can tell that it's not from that. And what we're very convinced by a number of things, it's actually a completely new kind of matter. It's matter that doesn't interact with light directly. It only interacts through its gravitational potential. That it may have, there are reasons to think it might be weakly interactive. So in physics, up until now, we only know of 4 forces. The strong force that hold nuclei together, the weak force that causes the things to decay, and in between is electromagnetism, that is the interaction of light. And then the last one is gravity, which is by far the weakest force, by many orders of magnitude, the weakest force. Those are the only 4 forces we know. It turns out, if those are the ones you allow, you would like this new form of matter to only interact weakly and gravitationally, as the 2 weakest forces, and then it would have all the right properties and could explain what we're seeing. But it means there has to be a whole new family of matter that we've never seen before, never created an accelerator or detected with, you know, looking in the cosmic rays or in, you know, material that we've searched around. We haven't seen it yet, but there are reasons to suspect it might exist, and there are huge experiments that will be going on, both to look at it coming cosmically and also at accelerators, but also these experiments looking at the orbits of stars and galaxies to try and determine more about its property. So this dark matter is truly a new substance in the universe that we need in order to explain what we're seeing. And we have many evidences that this must exist. Not only the fact that the orbit's around, and if you look at clusters of galaxies, you can see that there is definitely much more mass there than there is light, and even allowing that there's a lot of material in gas and in dust clouds and so forth. It's still off by at least a factor of 5, but there is a very interesting object that was discovered a couple of years ago called a bullet cluster. It's in the simulation I showed you a cluster that was very large and another cluster coming down, which I told you was coming down towards it, attracted gravitationally. This is one in which the clusters have actually gotten together and the cluster passes through. And the gases in the clusters collide because the gas is there and makes shock wave, and you can see it in the X-rays. You can see the wavefront in the X-rays, and the gas kind of stays there in the middle. And the cluster has gone through each other because galaxies are very small. That a galaxy is made mostly of stars, and it's mostly empty space. And so when 2 galaxies collide, they mostly just pass right through each other. The chances of a star hitting a star are very, very small, right? So the galaxies just go right through, right? And most of the times the galaxies don't even hit another galaxy. They just pass right through. So you see the galaxies out on this side. And then if you look at the galaxies that are behind those galaxies and see how much their light is bent, you find the bending of the light goes with where the galaxies are, not with where the gas is. And yet we know there's several times more ordinary matter in the gas than there is left in the stars, because in the cluster, the gas gets stripped out and spread into the middle of the thing. And most of what's in our galaxy or other galaxies is the gas and so forth that's going to be recycled and to make the next generation of stars. Yet, we see most of the mass, right, pass through each other just the way the stars did, compact and so forth, means that the chances of a collision is very small. Therefore, it's a very weakly interacting kind of particle, not like ordinary matter, which will scatter and interact. So we have many different arguments like that that tell us this dark matter is a completely new kind of particle that has, weak interacting properties, but has a lot of energy in it, roughly 5 times as much energy or more than in ordinary matter. And that's the framework in which we were able to build the beautiful universe that we see around us.
Oh, okay. Well, I have a lot more questions, but I think that's enough for now.
Well,
Thank you very much.
Let's see if there's another candidate. I hope that more people have questions. And then
thank you very much, sir. Appreciate it.
Well, thank you for your questions.
Have a nice time in Malaysia.
Hi.
Good afternoon. Sir, as you know, the 100 billion galaxies are present here, and it's are visible today and are arranged in non-uniform distribution. In this aspect, how we evaluate our measurement, the radiation pattern of light among such galaxies at different environment condition in the universe?
Okay. I'm sorry, I missed part. You were talking about the hundreds of billions of galaxies
Yeah,
and the radiation pattern of light from them.
Among the galaxies in universe.
Yeah, I'm still missing part of the question.
The radiation pattern, because these are visible and that are radiating the energy or light among the all. That's why what will be the radiation pattern between the galaxies?
Okay. So most of the light in the universe is the light from the beginning, from the very beginning of the universe. This thing that I have been using during my career to make an image of the embryo universe. Most of the light that exists in the universe, the whole universe is filled with a sea of light, and it's expanding and stretching the light out, but the light is still there. It is most of the energy and most of the light is in that radiation. Roughly about 1% more light is light from stars, right? So when the stars start burning, they start doing nuclear reactions, and for every time they do a nuclear reaction, they generally send out 1 photon that goes out into the universe and adds to the general light in the universe. And as part of the Cosmic Background Explorer satellite, the COBE satellite, we had an experiment to look for this light where you can look out from the galaxy out past the other galaxies and just sum up the total light coming from the early universe. And we found that there was roughly 1% more energy in the universe than in the radiation coming from the very distant universe, that is the first generation of stars and galaxies. And, the fact that we live in a galaxy means that in the galaxy itself, there's a lot more starlight. There's a lot greater density of starlight. But when you get away from our galaxy, it gets less. And so if you ask, in our galaxy, there's almost as much light and starlight as there is from the early universe. But between galaxies, it's a big factor, but almost a factor of 100 difference. There are other things that are out there, other kinds of light from particles colliding and from other things happening. But generally, more than 90% of the light and the energy that's out there is in the cosmic background radiation, the relic radiation. The rest of it comes from the galaxies. So the galaxies, even though there are very many of them, do not fill up all the volume of space, and they don't really produce a huge amount of energy, except when when you're living near the sun, you think the sun is very impressive, and it is, right? But when you compare that to how hot the beginning of the universe was, the entire universe glowed like the sun everywhere, whereas now it's only very small pieces of the universe that glow like the sun.
Okay. Another question is, what parameters you have on which you are going to develop a map for such galaxies?
Right. So the interesting thing was that the first thing you think when you see the map of the embryo universe is those small variations are the gravitational seeds to make galaxies, and you can predict what the galaxies should look like. Unfortunately, you're seeing only that at a radius that's roughly 14 billion light years away from you, and because of time constraints, unless you're willing to have a grad student who will work for 14 billion years, right, and make observations 14 billion years later, you won't see what the universe looks like now until 14 billion years more. And so you have to infer it by looking at intermediate steps. So you don't have a direct map that goes to the other map, although you can statistically estimate what it would be. But if you're willing to wait longer, you will see the galaxies from those original seeds show up, you'll see them as early galaxies and then as later galaxies. The longer you watch, the more you will see, except for the fact that the University